Welcome to this lecture on parasitology. Today, we are going to explore one of the most fascinating and medically significant parasites in the world, known as Taenia solium, or the pork tapeworm. We will uncover how this organism survives, the dual threat it poses to human health, and the mathematical tools epidemiologists use to track and control its spread. Let us dive in. To begin our journey, imagine a long, segmented ribbon living quietly inside your intestines, absorbing the nutrients from the food you eat. This is the classic behavior of a tapeworm. However, Taenia solium, commonly known as the pork tapeworm, has a much darker and more dangerous secret. It possesses a terrifying dual personality. If a person accidentally consumes its microscopic eggs instead of the larval cysts typically found in undercooked pork, the parasite becomes confused. Instead of staying in the gut, it travels to the brain or muscles. Understanding this dual nature is the first step in defeating it. Now that we understand its dual nature, let us look at the physical structure of this parasite. Taenia solium is a flatworm belonging to the class Cestoda. To anchor itself in the human intestine, the adult worm uses a specialized head structure called a scolex. This scolex is equipped with 4 powerful suckers and a rostellum armed with 2 rows of sharp hooks. Behind this formidable head trails a long chain of reproductive segments known as proglottids. Each of these segments is essentially an independent reproductive factory capable of producing thousands of eggs to continue the parasite's life cycle. Building on our knowledge of its anatomy, we must examine how this parasite survives across generations. Taenia solium is a zoonotic flatworm, meaning its life cycle inherently links animals and humans. It strictly requires 2 different hosts to complete its development. Pigs serve as the intermediate host, harboring the larval stage of the parasite in their muscle tissues. Humans, on the other hand, act as the definitive host, where the parasite reaches full sexual maturity as an adult tapeworm in the intestines. This intricate biological dance between humans and pigs is what allows the parasite to persist in the environment. This reliance on 2 hosts leads us directly to the 2 distinct diseases this parasite causes in humans. The outcome depends entirely on which stage of the parasite is ingested. When humans consume undercooked pork containing larval cysts, the adult tapeworm develops in the intestine, causing a relatively mild condition known as taniasis. However, if humans accidentally ingest the microscopic eggs shed in human feces, a much more severe disease occurs. The larvae hatch in the stomach and migrate to various tissues, including the central nervous system, causing cysticercosis. This distinction is absolutely critical for medical diagnosis and treatment. Having discussed the 2 diseases, let us visualize exactly how they occur through this life cycle diagram. On the left, you can see the standard cycle. A human, the definitive host, eats undercooked pork containing cysts, leading to an intestinal tapeworm. This human then sheds gravid proglottids and eggs into the environment. Below, a pig ingests these eggs from contaminated vegetation, becoming the intermediate host. But look at the right side of the diagram. This shows the accidental fecal-oral route where a human ingests the eggs directly. The arrows clearly show the larvae migrating to the brain and muscles, resulting in the dangerous condition of cysticercosis. Seeing the life cycle visually helps us grasp the immense real-world impact of this parasite. Understanding Taenia solium is absolutely critical for global public health, especially in developing regions with poor sanitation and free-roaming pigs. The most severe consequence, as we just saw, is neurocysticercosis, where larval cysts lodge directly in the human brain. Tragically, this condition is the leading preventable cause of acquired epilepsy worldwide. It devastates entire communities and places a massive, ongoing burden on fragile healthcare systems. To break this cycle of poverty and chronic illness, epidemiologists must find ways to measure and control the spread. To effectively control this spread, public health officials need to quantify the threat, which brings us to our first mathematical model. Parasitologists calculate the daily environmental contamination rate to understand how quickly a single human host can infect an area. The formula is E equals P times N. Here, E represents the total number of eggs released into the environment per day. P stands for the number of gravid proglottids shed by the tapeworm daily. Finally, N represents the average number of eggs contained within a single proglottid. Conceptually, this tells us that environmental risk is directly proportional to both the shedding rate and the worm's fecundity. If either the number of shed segments or the egg count increases, the total contamination skyrockets, drastically raising the risk for the community. Now that we have our formula, let us apply it to a concrete clinical example. We are given a patient infected with a single adult Taenia solium tapeworm. This patient sheds an average of 5 gravid proglottids per day, and each proglottid contains approximately 40,000 eggs. We need to calculate the total daily environmental contamination rate. We start by writing our formula. E equals P times N. We substitute 5 for P and 40,000 for N. Multiplying these together gives us our final answer of 200,000 eggs per day. Physically, this staggering number means just one untreated person can release 200,000 highly infectious eggs into their surroundings every single day, creating a massive biological hazard. That staggering daily egg output explains why outbreaks happen, which leads us to how we measure the scale of those outbreaks. When a community is exposed to such high environmental contamination, health officials must determine how widespread the infection has become. They do this by calculating the disease prevalence rate. Prevalence is a fundamental epidemiological metric used to measure the exact proportion of a population that has a specific disease at a given time. By standardizing the infection data into a percentage, officials can compare the severity of outbreaks across different villages, regardless of their population size. This metric is absolutely crucial for deciding where to allocate limited medical resources, like mass drug administration. To calculate this standardized metric, we use a very straightforward epidemiological formula. The equation is R equals C divided by T, all multiplied by 100. In this formula, the variable R represents the prevalence rate, expressed as a percentage. The variable C is the number of confirmed cases of the disease found in the area. The variable T represents the total population at risk in that specific location. Conceptually, dividing C by T gives us the decimal fraction of infected individuals. Multiplying by 100 simply scales that fraction into a recognizable percentage format. If the number of confirmed cases increases while the population stays the same, the prevalence rate will naturally rise, signaling a worsening outbreak. Let us see how this prevalence formula works in a real-world public health scenario. In a rural village of 1,500 people, medical tests discover that 45 individuals have active Taeniasis. We need to calculate the prevalence rate to see if it exceeds the 2% threshold for mass intervention. We start with our formula, R equals C over T times 100. We substitute 45 for C, the confirmed cases, and 1,500 for T, the total population. Dividing 45 by 1,500 gives 0.03. Multiplying by 100 yields our final answer of 3%. Because 3% is greater than the 2% threshold, officials must immediately initiate mass drug administration.
We have covered a tremendous amount of ground today, so let us review the most important ideas. First, Taenia solium is a highly adaptable parasite that causes two distinct diseases, teniasis, from eating larval cysts, and the much more dangerous cysticercosis, from ingesting eggs. Second, we learned how to quantify the parasite's threat using the environmental contamination rate and the disease prevalence formulas, proving how simple math guides critical public health policies. Finally, breaking this transmission cycle requires a combination of medical treatment, rigorous meat inspection, and systemic improvements in sanitation. You now have a solid foundational understanding of this complex parasite.